So I'm going to talk about what we are doing right now at Betsson Group to scale our architecture. And if anyone wants to see the code samples or play with this at home after the presentation, you can go to this link right there, github.com/rogeralsing/presentations. And then there's a folder called LeetSpeak, where all the code samples and scripts, etc., for everything I'm going to show is located. So, some short info about Betsson Group. We have 21 different brands across Europe and Latin America and Central Asia. And during the second quarter of this year, we had over 500,000 active players on the different brands. There's a lot of manager crap on here, so let's ignore that for now. So what to expect from this talk? I will talk a little bit about the history, where we came from in terms of architecture, and a lot of geekery about microservices and service discovery, Docker and .NET Core. So it might sound a little bit like buzzword bingo, but I'm going to try to show how to actually make all of this work together in a meaningful way to actually use it for real. I'm not going to talk about Aka.net, and I'm not an ops guy, so if anyone has any tricky networking questions for Docker or anything like that, I'm not the guy to ask. So, with that being said, in the past, we started out with one brand and one system. So the brand was Betsson, and the system was this classic monolithic application. So it was a huge, clunky system where everything was interacting with everything. And there was a lot of different subsystems, like we have a wallet subsystem and we have a customer subsystem containing all the customer details, etc. Campaigns subsystem, which keeps track on what campaigns your user belongs to. But over time, we acquired more brands. So now we had, I actually don't know if these were the exact brands we acquired first, but we got new brands and we had this huge clunky system, this monolith. So how could we scale this? How could we make this work for multiple brands? So if we look at what Martin Fowler and James Lewis wrote about monolithic applications in their article about scaling, they wrote, a monolithic application puts all its functionality in a single process and scales by replicating the monolith on multiple servers. And that was exactly what we did back then. So we created the concept of instances, and one instance is really one or more servers. So we took the same monolithic application and then placed it on different servers. And you have to take into account that when we started to acquire brands, business usually moves faster than technology, so we couldn't really just rewrite it the way you should have. So we had to come up with a solution, and this was one solution. So we could take a single brand and place that in a single server, for example, or take multiple brands like A and B and place that on a single server. So we sort of partition on a brand level and say that BetSafe runs over here and Betsson run over here. And and over time, service-oriented architecture became sort of the thing everyone should do. So we started splitting up this monolithic application into smaller chunks. And by looking at this diagram, you might think that this is on the way to microservices, but it's in no way, shape, or form microservices here. It's really, really big systems still, even if they are sort of divided. Each of these blocks could easily be between 50 and 100 .NET projects. So it's still huge chunks of code, but still better than this gigantic monolithic thing. So what challenges have we had with this past architecture? One challenge is that we are heavy consumers of message queues like N-Service Bus and MSM queue. And in the MSM queue world, you can't really have competing consumers on the same queue. So we have systems where we have one subsystem sending messages and a single subsystem pulling messages out of this queue, which means that we don't have any redundancy for those consumers, as we can only have one per queue, so to say. So that doesn't scale very well. Another problem is that we have had shared servers, and shared servers leads to a problem called noisy neighbors, because if you have a lot of different systems, different services on the same computer, let's say that this customer service starts hogging up all the memory or CPU on this machine. There's nothing left for the other services, so one service can affect another service. So it's hard to track this problem and prioritize in backlogs, etc., because this customer service might run just fine, even if it eats all the memory, but some other service might be down, and who should fix this problem if the gaming service is down because of the customer service leaking memory, for example. So that is one problem we have seen. Another issue we have had is single point of failure. Since we only have one of some of the services because of the single consumer problem, if the one service we have, if that is down, then it's down. We don't have anything to replicate to. We don't have any fault tolerance or redundancy baked into the system due to this single consumer limitation. And the same issue really applies to deployment, because if the system is down, then it's down. We can't take any load during this time. So when we want to deploy, we need to first kill the services, then install it, and then start it up, and then we're back online again. So that doesn't give a really nice customer experience, because you can't really use those services when you're playing, when that happens. So to recap, the challenges with this is scalability and elasticity, because of these single consumer problems. Isolation, we have had resource leaks, and that's definitely a big problem. Availability, if the one instance of one service is down, then we're of course not available, so that's a problem. And deployment is a problem, because we need to take things down and have downtime during this period. So to move over to the current architecture, we are moving towards a microservice architecture. So if we take these services we have had in the past, what we want to do here is to actually take this service and split it up into multiple smaller chunks. So instead of having this huge yellow bean over here at the customer service, then we split it up into different services, for example, login, registration, and customer data, for example. That allows us to actually scale the individual parts without scaling the entire thing. Maybe the login service doesn't need to scale as much as the registration service, for example. So if we again look at what Martin Fowler and James Lewis said in their scaling article, is that a microservice architecture puts each element of functionality into a separate service and scales by distributing these services across servers, replicating as needed. So that sounds simple enough, right? Because if we just have all of these services floating around here. But what do we actually need to do in order to make this work? Because now we just have this sort of puzzle which doesn't fit together. How can we make this guy over here talk to this service down there? There needs to be some way for them to find each other and interact. So that introduces the concept of service discovery. So if we have the same services, A and B, and we have some sort of service registry, when you start up your services, they can register themselves into the service registry and say, hey, I'm A, and hey, I'm B, and I'm at this IP address, or I'm at this IP address. So the service registry knows about all services active in the system right now. And once the data is in the service registry, then other services can query for that data. So for example, if service A wants to talk to service B, it can now send a request to the service registry and say, hey, where is the instance of service B? And the registry can reply and say, it's over here at this address. And once service A has this knowledge, it can start calling service B. And the nice thing about this is that it actually works with multiple instances. So we can have multiple instances of the same services. We can have service A 1, 2, 3. We can have service B 1, 2, 3. And they can all interact with each other. So even if instance B1 is down, there is still B2 and B3 that can take its place. So we have the fault tolerance built into the system there. And back in 2014, at LeetSpeak, pretty much exactly 2 years ago, I think, Niklas Gustafsson from Spotify was talking about the same topic, how they scaled Spotify. And they used the concept of service discovery on a DNS level. So their service registry was the DNS. So their services created DNS records when they started up, and then they refreshed those DNS records over time. And if one service went down, it couldn't refresh itself in the DNS anymore, so that was sort of removed from the DNS routing. We are looking into a product called Console from HashiCorp. And just to give you a hint on what Console is, gonna paste it in there. So Console is this service discovery product, and it also has a little web dashboard. So you can see here what services are currently active in the service registry. So in this case, there's a service called Console, which is the service registry itself. And there's also a Redis and a web service registry in here. And if we click one of these, we can see that there are 3 instances of the Redis server. So you can see all the different instances of each service that you have. And if one of the services is down, you can see that it will fail its health check, and it will be in different colors. So it's a nice tool to see what's actually going on. Oh. Then I have written this really small library called Microphone, which is really just a client for .NET to Console. And what Microphone does is that it acts as a client library, and when your service boots up, Microphone will call into Console and say, hey, I'm service customer or wallet or whatever. Microphone also contains this health status endpoint so that Console can ping back to your service and ask, hey, are you still alive? Are you still alive? And as long as the service works as intended, it will return 200 OK status code, and Console will see that, well, this instance still works. You can also use Microphone to query Console for service locations. So you can say, where is the location of service wallet? And Console will return the different addresses known for this service. Or you can just ask Microphone to bake the entire URL for you and load balance on a software level. So that is pretty nice. So Console will enable these features. You don't automatically get scalability just by having Console, but by having Console, you can locate different services in your cluster of machines. So it helps in the scalability department. It also helps with availability, since you now can have multiple instances of the same things. And console also do these health checks to see that every instance is actually okay. Another feature you will get is there's a scalability pattern called circuit breaker, which means that if one service is down, then the circuit breaker will hit and say that you can't talk to this service anymore, so it's removed from any load balancer or ability to call it. And you get the same thing here, really, because if a service starts failing a health check, then it will not be in the response when you query for that service. So if a service is overloaded, it will fail its health check and be removed from the load balancing for a while until it can get back online. Console also has the concept of a distributed configuration. That is a bit outside of scope for this talk, but it does have that, and it's a key value store where you can have configurations and things like that. So instead of having your configuration in web config or whatever, you can actually have the configuration spread across console, and console can even push changes to you when a change occurs. So you can actually have systems having their configuration updated as your system runs. So a little bit about ASP.NET Core. Betsson Group has traditionally been very Microsoft focused, so we come from the full .NET stack, which is sort of unorthodox for a companies in the scalability department, because scalability have historically been more in the area of Java or Erlang and Go and things like that. Not as many companies use .NET for that kind of applications. But that is about to change now that we have ASP.NET Core and can run in Docker, for example. So I'm going to show a little bit of code. So is this large enough to read? Yeah. So microphone is a NuGet package on the official NuGet, so you can just reference it if you want. And it worked for classic .NET and .NET Core also, so it doesn't matter where you want to use it. So I've said that I want to use it for ASP.NET, and I want to use the console provider because it's agnostic to the actual underlying service provider. You can use etcd or Zookeeper or whatever you want, but we're going to use console. And in ASP.NET Core, you have these startup settings where ASP.NET configures itself and say, I'm going to use Kestrel, I'm going to run on this address, I'm going to use these content folders, etc. Then you can add some code to say, when you configure your services, you can say that I want to add microphone, and I want to add microphone using the console provider. Then we can also configure the console provider to say what host it should find console on. If you run console sort of bare metal, if you run your services and console on the same machine, then you can of course use localhost here, but I'm going to show some demos using Docker. So we're going to have our service in one container and console on another. So we need some way to find the IP address to the local console agent. Then you also need to say that you want to register this service using microphone. So this is the name of the service we want to register. So in this case, the service is going to be called service 1. And we also need to tell console of the public address of this service so that other services can actually find it. Because if I would just put in localhost here, if someone on another machine queries for this service and they get localhost back, things will not work as intended. You need to take the accessible address and place it there. I'm not going to run this right now. I'm going to show that later. So this brings us to Docker. And when I started reading about Docker a few years ago, I was a little bit confused of what's the actual purpose of it. Is it just a way to package applications and run them? Or where is the actual benefit from this? What's the business value of having Docker? And one of the features that you get by having Docker is if we take the same services we had before and run this on a server, we had the potential resource leak. If one of the services eats all the memory or all the CPU, then that will affect all the other services. By having Docker, you can have isolation around each individual service. So you can say that this service is only allowed to use 25% of CPU and 25% of memory or something like that. So if the service runs amok and takes more memory than it should, only that service will fail instead of having other services being affected, which I think is really great. You can argue how strong this isolation is, but it's better than nothing, absolutely. So I think it's a really great feature for this. Another thing that you also get is Docker Compose. And Docker Compose is, I think of it like a recipe for a service or for a microservice, because you can say that I have my service, and this service maybe needs some database, maybe it needs Couchbase, and maybe it needs some sort of load balancer, maybe Nginx or HA proxy or something like that. Then you can use Docker Compose to script that and say, when you start this service, also start these other containers together with that. So we're going to take a quick look at that. So here I have a Docker Compose file for console, and this is what we're going to run later to set up our cluster of machines and service discovery. So we can see that we have a service called console agent, and it's going to be based on the Docker image called rogeralsing/console and the latest version. It will also have a link to console 1. Console 1 will be one of the servers we have, because console is a cluster software. So you need 3 or 5 servers, and the agent needs to know where to connect to when it starts up. We can see that we have console 2 and console 3 and console 1 down here. So we have 3 servers configured with different configurations, and we also have the agent which will run on all client machines, because I can tag my servers with different key value pairs. So I can say that this machine is a server, or this machine is a worker, or this machine is a front-end machine, or whatever. So I say that the console agent should run on all the client machines. And that brings us to cluster schedulers. In the Docker world, there's a bunch of different cluster schedulers. For example, there's one built into Docker called Docker Swarm, which are those whales here. There's another from Google called Kubernetes. And Kubernetes seems to be the cluster scheduler that is becoming the de facto standard. So if you're interested in this, you should definitely start looking into Kubernetes. There's another called Mesos, which also can schedule Docker containers. And then there's a product called Rancher, which has its own cluster scheduler called Cattle. So they have this little cow here. And what cluster schedulers bring you is that instead having to reason about your machines, that I have these individual machines and I want to install these services here, here, and here, You can instead reason about it as having this huge resource pool of memory and CPU. So when you say that I want to run 3 instances of the registration service, for example, you don't really need to say I want to run it on server 1, 2, and 3. The cluster scheduler will find a place for this service to run by itself where there is room and try to balance it as good as possible across the different servers. Putting it all together, I'm going to show some demos on how to actually do this and how to actually run ASP.NET services in a cluster environment with service discovery and all of that. So we'll start by taking a look at the Rancher UI. And Rancher is this product which is both a user interface, it has this cluster scheduler, the cattle one, and it's also a operating system, because if you're going to run a lot of different Docker machines in a cluster, then you don't want the base operating system to utilize a lot of resources. You want a really slim base operating system. So Rancher has its own called Rancher OS that you can use. That being said, let's take a look at our machines. So I have 5, 6, 7 machines here. I have bull 1, 2, 3, and cow 1, 2, 3, 4. And these machines have different tags on them. So we can see that the bull machines have console role server, and the cow machines have console role client. And in a traditional infrastructure, if I wanted to run all of my services on these machines, then maybe we had some ops teams installing software on each server, and it's clunky and hard to move fast. So let's see how we can do this in the Docker world. In Rancher, there's this concept of a stack, and a stack, you can think of that as a single microservice with all things that are needed together. So we can take this Docker Compose script. So I take this script, which is my recipe for how to set up console. And I say add stack, and we can call this stack console. And I paste in my Docker Compose script, and I click create. And we can see that Rancher is now trying to install each of the services across my machines. So we can see that console 1 is now up and running. Console 2, 3, and the agent are booting up. And if we take a look at the different machines, we can now see that things are starting to happening on the different machines. So console 2 is on bull 1, console 3 on bull 2, and console 1 is on bull 3. I didn't have to specify anything on where to actually run it. This was completely handled by the cluster scheduler. And we can see that on all of the client machines, we have one of these console agents running. So things seems to have started. We can now see that everything is up and running. I can open up this console web UI that we saw before. And we see that the console service is running. And if I go to nodes, we can see that console is now aware of all my machines here. So we have bull 1, 2, 3, cow 1, 2, 3, 4. So all of the machines are available to the console cluster. Let's say that I now want to install my microservices on top of this. First of all, I should just show my microservices so you know what I'm actually doing. I have 2 ASP.NET services. Both are using this microphone library to interact with console. And service, let's start with service 2. Service 2 has this API controller called hello controller. So the only thing that one does is it has a get endpoint, which returns hello from service 2. Then we have service 1, which has a controller called aggregate controller. And what we're doing here is that we are actually showing how to interact with other services using console or microphone. So we are injecting this iCluster client, which is an interface in the microphone library. Then we use that to resolve a URI to service 2. We don't know where service 2 exists. We just say that I want to have a URI that is valid for service 2. And I want the URI to end with these elements. So we'll get the address of service 2 and have the rest of the URL appended to it. Then we say, let's create an HTTP client, set the URI, call the service 2 endpoint, and return a string just saying got result from, and then the URI of the service 2 that we resolved. So not super fancy, but at least it will show that things work. So I also have this Docker Compose script for my services. So we can see that service 1 will listen to port 5000. I have already pre-packaged my services in Docker. And I do the same for service 2. And we can see that these services will start on the client machines. So they will not run on the console server boxes. So if I take this, and then I say add stack, my microservice, and then I just paste in the Docker Compose script for my services. What will happen now is that Rancher will actually pull down my 2 different images and try to start them individually. And what we can do here is actually we can peek into them and see what is going on here. So in Rancher, you can actually view the log files of the underlying container. So we can see here that the service is up and running, and console is actually doing health checks against my service. So it is calling into my service and saying, hey, are you still alive? And my service will say, yeah, I'm okay. So if we now go to our console interface again, we can now see that service 1 and 2 are now registered in the console register. So if I click service 1, we can see that service 1 runs on cow1. So this is the IP address to service 1. Whoops. And service 2 runs on cow3 with this IP address. So let's see if we can actually access these services now. Stacks, and we can see that service 2 is running on this port. So if I click here and we say status, which is the health endpoint for my service, this is the endpoint that console is pinging constantly to see if the service is alive. So we can see the name of the machine and the response was okay. So let's see if we can actually communicate with the hello endpoint. And we can see that we're getting hello from service 2, which is not super interesting. If we take service 1 now, and we do the same thing, API and aggregate, we can see that service 1 have now talked to service 2 on this address and called this endpoint and got this result back. So without having any hard-coded dependency or configuration between service 1 and 2, service 1 could still find service 2 and talk to it. And this might not be super interesting as long as we just have one instance of everything. But if we go forward, if we want to scale our services, let's say that I want to run 3 instances of the service 2. What I can do now is I click on this, And everything I do in this interface can be done either via a REST API for Rancher or via a command line tool that they have. So you don't need to do this by having someone sitting actually clicking. You can have your DevOps team actually doing this scripted or having tools for this. So here we can see that service 2 has a scale of 1. If I click this one and say, I want 2 of this, now the cluster scheduler will try to find a good place for the second instance to actually run. And let's say that I want 3 instances of it. Now boot up. If we go back to the servers and take a look, we can see that we have service 2 running on cow 2 down here. And service 2 is also running on cow 3 and on cow 4. So we now have 3 instances of the same service. And supposing that everything works as intended, we should now see 3 instances of the same service here in console. So we can see that service 2 exists on this address and this address and this address. And all of the instances are healthy. So if we go back to this service 1, which actually talks to service 2, if we now refresh this, we can see that we get different addresses back when we refresh, because console will return 1 of the 3 healthy instances of service 2, and microphone will just load balance across those different instances. So what we can do, just to show that we actually have a fault-tolerant system now, is that if we go in here and say, I just want 2 instances, we kill 1 of the instances. Imagine that as if 1 of the instances had crashed for whatever reasons. We should now see that in the console UI. We can see that 1 of the instances are now no longer healthy. This means that this instance will not be included in the list of addresses when service 1 tries to communicate with service 2. So if we refresh here, we will just see 2 different addresses instead of 3, because it has been removed from the load balancer. So let's scale this one back up to 3 again. Another really cool thing that you can do with this, since we have multiple instances of the same service running, is that we can actually deploy this service as the system is running. Because if we have 3 instances, we can bring down 1 of the instances and reinstall that while the other 2 takes the load of the first one. So if we go back here and here, then you can say, I want to upgrade this service. I want to pull down the latest image of this service. Now it will actually be the exact same because I haven't republished anything, but just to show you how it works. So you can say that I want to upgrade 1 of the instances at a time with an interval of 10. So it will upgrade 1, wait 10 seconds, upgrade the next 10 seconds. So if we do this, now Rancher is actually pulling down 1 of the instances and killing that and starting up another one. But since we have console here knowing about healthy instances, our system is still up and running. So I can upgrade 1 of these instances while still having successful responses from my service that talks to service 2. So we can see that we now have 5 containers. That means that we have 3 of the old and 2 of the new containers, where 2 of them have been stopped. Now we're up to 6, and in a little while we'll see a checkbox, and we can say upgrade finished, and now we are running only on the new version of the service. So that's a pretty nice way to have zero downtime systems that you can deploy in production. Another thing that is kind of important in this area is that, at least for us, which have a huge code base in old .NET, we can't move that code base into Docker just like that. We need to migrate service by service into Docker. So that means that we need to have the Docker services compatible with the legacy services at the same time. And since we have console running, we can actually make the legacy services register in console also, and as we're only exposing the public endpoints for each service, all of the services can communicate with each other. So it doesn't matter if some of the services are actually in console or some of the services are on bare metal machines outside of Docker. You can still have them integrate with each other. So that was one of the really important aspects for us, at least. Some more stuff that we're looking into, but which is a little bit out of scope for Docker and this talk really, is selecting a proper tech stack. As I said before, it's a bit uncommon to actually build this kind of systems on .NET. You can do it now with .NET Core, but still the tooling and the ecosystem around other platforms is kind of nicer. So we are looking into Go and also Elixir. So why are we looking at those two specifically? Is because they are both built for concurrency. They have really nice concurrency support built in. We have some support in C# and .NET with the task parallel library and async await, but it's nowhere near as nice as it is in the other languages. They are both also built for distributed systems. So the tooling, the ecosystem, the communities are more mature for this kind of systems. So I'm not trying to bash .NET for that, but if you're going to build really big and scalable systems, I don't think .NET is the absolutely best place to be. Another super important aspect that we are looking at together with this is once you start building microservices and going to scale out with multiple instances of the same services, is that you need some way to monitor your systems. So there is a really nice project started at Twitter called Zipkin, which is a distributed tracing and logging framework or platform. So you can run Zipkin and let your services talk to Zipkin and say, hey, this is a current service executing, and now I'm calling this other service. So this lets you see the entire call trace, what services has talked to other services. You can see the exact offset in milliseconds when some service started to execute. So it's a really nice way to actually see what's going on in a distributed environment, because if you don't have logging and tracing, you're going to have a really hard time to actually maintain your distributed system. So if anyone is going down the same route as we are, definitely take a look at Zipkin. And I'm actually contributing this UI right now to Zipkin, so I'm trying a bit of front-end development for a change, but I think it's turning out quite nice. And that is everything I have today. So, questions on anything? Yeah? Yeah, either you have to register with a different name or you have to version it as you would version any standard service. Even if you just have a single instance, maybe you need to have version 1 of your contract still available, at least for some period of time. So console and service discovery doesn't really solve that part for you. You still need to maintain your API contracts and all the normal procedures for services. But in theory, you could register it as a new service with a different name and have new clients talk to the new service. Yeah. Thanks. Yeah. We are using hardware load balancer on the outside of the system, so we only use software-based inside the system itself. So we are still going to have real load balancers towards our customers and integration partners. But having a software-based load balancer inside the system is kind of nice because it takes load off the actual outer load balancers, and the software-based load balancing, where you just take one of the available endpoints for a service, is often enough for your internal services. So I don't know if that answers your question, but we use both approaches for different purposes. Yeah. They are completely standalone, so you don't have to have any specific protocol or anything. You could build them as HTTP services, or you could have gRPC or akka or akka.net or whatever you want, as long as you have something that can call into console and get the address of a remote part and then talk to that. So it's not connected to the protocol or media that you're talking at all. You just use console as a lookup. Yeah.
How do you ensure that your service registry doesn't become the single point of failure?
You can configure your services in Rancher, for example, and say that I want always at least 3 or 10 or whatever number you want for a single service. So even if one of the instances of that service dies, then you still have 9 others that can take the load. And supposing that console does its job.
But in your code, you had a line startup host value. That's what you were sending as an address of your service registry. Isn't it the single point of failure? You're sending just one address.
No, what we do here, I can show you exactly here. Rancher has this built-in metadata API. So you can query Rancher for what is the address of the current container executing. So if I have a service executing in a container, I can ask Rancher what is the address of my container. And that address is what is going to be registered into console. And if you have 10 different instances, all of them will ask Rancher, what is the address of me? So you will have 10 different addresses that are registered in console. So we can see that in the console UI here. We can see that service 2 runs on this address, and oops. So there are different IP addresses for each of the instances here. So even like in this case where this specific instance is dead, it's just that address that is no longer active. All of the other addresses are still available. So when you query console and say, hey, give me one of the addresses to service 2, you will get one of the healthy ones. Yeah.
Can you scale your services to be more than the number of machines you're having? Shouldn't that impact performance?
Yes and no. We are doing port mapping because we need to be able to integrate with outside legacy services. So we need to port map our containers to the outside world. That means that only one instance per server can run on this specific service because you can't have two instances listening to the same port. If you don't do that, then you could really have as many instances as you want on a single machine. That usually don't make much sense if you build in any real language. If you use Node.js, for example, which is single-threaded, then maybe it's useful. I don't know, but Node.js just runs on a single thread, and if you have like 8 cores in your machine, maybe you need to run 8 instances. That's more than I know about Node.js, but supposing that your services can utilize the resources they have available, you shouldn't need more than one per machine, so to say. You can also configure the services to run on any number of machines. So let's say that we have machines with different tags, for example, the console client machines. Then you can say, I want one of the console clients on all of the machines with this tag. So you don't need to specify a given number. You don't need to say 3 or 10. You can just say, run it on all of these machines. Yeah?
I'm just curious about your build targets, the build service. Do you create the Docker image, or what do you do?
Yeah, currently, nothing of this is in actual production. This is bleeding edge from our labs, so to say. So every image are built manually just from the dev environment. But you can actually build the Docker images either by Docker Hub, or if you have this local registry, so you can have hooks that listens to GitHub or Bitbucket or whatever you use, and make that trigger a build of your image. So depending on how you want to use it, you can use different approaches. But I like the concept of being able to test run it on my local machine, because I want to see that I can actually run multiple instances. So I usually build locally just to see that it works.
So is console itself scalable?
Yeah, we can actually see that here in the... We can see that we have the 3 different console servers, and usually you have 3 or 5 depending on load. And HashiCorp, which creates console, they have clients that run like 5,000 machines in a single console cluster. So that is probably more than most of us will ever need. But it certainly can scale to that size. Then you run one of these console agents on each worker machine, so to say. And it's all peer-to-peer based, so all of the machines have the same information. So even if they disconnect from the server, they can still have stale data that is active. Yeah.
So how are you load balancing, for example, are you using software also like
Yeah, the easy answer from my part is that at the section where I work, at the Stockholm office, we only do back-end stuff, so we don't do any front-end. But you can easily use, I can show you here. We can actually say add load balancer, and I want to have a load balancer on 5001, and I want the load balancer for service 2, for example. This will create a, oops, need a name for this one. So this will create a software-based load balancer using HA proxy and configure that correctly to talk to service 2. So you can have software load balancers in here, and let's see if it has started. Maybe I didn't specify the target port in the... I misconfigured it. Yeah, I need to delete it. But you can set up this kind of load balancer, or you can easily just have a standard load balancer, a hardware load balancer that just redirects to your images. Yeah, and that's definitely outside of what I do. So I'm not an apps guy, so I can't really answer that. But of course, you can set up health checks for your load balancer and see if the same way as console do health checks against your services, your hardware load balancers can do health checks against the services too. Yeah. Simply because we are more comfortable with the console. It shows you what's going on. It's easy to get started with it. So, yeah, okay. You mean the console DNS? Yes. We are discussing actually using that because that's really nice for legacy applications and be able to just not touch them at all and they just work. But then we need to pick a fight with the ops team, so it's more in that area. In the services, you mean? Yeah, this doesn't take into account anything about any clustered servers or databases. You can definitely run those outside of Docker or wherever you want and just connect to them as any ordinary service. I think we're running out of time here. One more quick question from anyone? No? So thank you from me.